Hello, wherever you are. This is going to describe how we can reduce and collect data for observations of a cluster, radio observations of a cluster of a galaxy cluster, and separate out diffuse halo emission from various compact features. The actual individual scripts sometimes require a .csv file. An example of which is shown up in the screen in our left-hand corner here. Basically, this is kind of a residual from a project I did together with Hans Andernacht on searching for giant radio galaxies, and you might have, say, 40 or 50 or more individual giant radio galaxies that we were looking at, and unfortunately, we still need one of these things for just looking at individual clusters. You certainly don't want to try and look at more than one cluster in the CSV file. Basically, all the CSV file has a specific central frequency for various reasons. Then just the name of the source, RA and Dec in degrees, and all this stuff at the end here, especially like the angular size here is for search radius for giant radio galaxies. But then we have in the case of our Abell cluster, we know the redshift, and the minus 0.8 is a spectral index, which we use for guesstimating things like various source parameters. So we're now going to execute this thing called example script. First thing we're going to look for is to use morphological analysis, which there's an introduction to that in this script from Larry Rudnick, and you can also look on Wikipedia for a description of what's called mathematical morphology. Anyway, we're going to use mathematical morphology to separate out diffuse and compact sources in the AbellS1063 cluster. So I'm going to start up the script. And those parameters, and what we've done here, we've run the separation script where we've essentially, let's just raise the size of this a bit. So using mathematical morphology, we've separated the area into diffuse emission here, which we can see, and otherwise what we have are essentially the point sources in the region. And we started that we had a threshold of 6 sigma, which was the clip level, which we used to separate out nominal point sources from diffuse emission. But there's still a few little sources in here which we would really like to copy back into the diffuse sources for some later analysis like flux densities and so on. So let's just zoom in here a little bit. And then we can click on this. Let's zoom out. And then we can click on this down here. Click on that. So second lobe. Go back. So we've essentially selected 2 areas where we want to copy them from the point source thing over into the diffuse section. And to do that, at least with matplotlib, you seem to have to shut down the plot first before you can send any data out of the matplotlib program to the downstream program. So we're just going to close it. Now what we've then done is that we went through a couple of operations there very quickly. We went and did what's called in-painting. Now, in-painting uses a method called Navier-Stokes analysis to essentially fill in the holes. You might have noticed in the previous image here in our central part of the image, we had holes which were drilled through because of the point sources. We've now used an in-painting technique to take the surrounding diffuse emission and smooth it and paint it into the areas where we had holes. And so, and also now you'll notice that because I clicked on those 2 sources, we now have these 2 sources as part of the image shown here. So what we're now going to do is, once we've filled in the area, we can see we've got, we want to actually now then determine the integrated flux density for the diffuse component here. So we'll just click on that. And there's a lobe one, so we can, what it'll do then is go off and process the flux. Now, after we process the flux, or getting the parameters for the unconvolved image, there's a function. You run a program called get galaxy parameters with various things, such as the name of the CSV file again. The threshold for integrating the flux is now 3.5 sigma. You won't worry about this parameter, but set it to false, because you do not want. There's an option for radio galaxies where you delete potential nuclear sources in the image from the diffuse image. Then we went through a convolution step where we have convimage.py, and it says just the name of the file that we're going to process. And there's a lot of default or not default images, parameters. If you look in convimage underscore pi dash help, it'll tell you all the possible parameters. Default is to actually convolve the image by a factor of 2. And then we can then, again, this is now the convolved image, and we'll just do this guy. Let's see, we can expand this thing. So we just want to look at this central image again here. Now, one thing you can do if you want is, again, we can get, this is again looking at the default image, but let's see, we can get down here. If you don't like the sort of levels that we're now going to specify an area of this image using a manual procedure. If we don't like the thresholds that have been generated for you directly as how many sigma, you can actually say that you can actually have a flag saying dask mask equals false, which says we don't want to actually use a default mask, but I want to draw these things myself. So we can actually draw bounds where we might test whether diffuse emission actually is. And you don't have to, if you draw a boundary like this, then the convolution or the polygon analyzer will know that this is the end point, and it'll automatically join the points together. And so if we've done that, we can shut the thing down, and it'll go off and convolve things. Now, you'll remember that way back when we actually subtracted out the diffuse emission, but we had all these point sources left behind. So if we want to get flux densities of each of the point sources, we can again do that by, let's see, we're going to zoom in here a bit. The area we're interested in is just these sources here. So I can select the sources I want to get flux densities for by clicking on here, here, and here. So we get 3 objects. This radio source, by the way, I should have commented on this thing earlier. This source here is a little head-tail galaxy in the cluster. This source here is actually the source of the central lensing galaxy in the cluster. And this is actually kind of there's actually a source on the edge of the giant central object, which this is actually a lensed galaxy in the background. It has this computer distortion because the actual Einstein lensing is starting to stretch this thing out. So anyway, we'd like to know the flux densities of these three sources because they can be used then to compare and get spectra from other observations of the source. So we've got three objects there. Now I want to look at some of the output of this thing. So, sorry, let's see here. Okay, so let's look in the compact sources that we just listed. Now this is something again which has some influence from the search for giant radio galaxies. The Shapley package, which we use to define contours for the analysis, also has sort of a super polygon things, and if you specify multiple polygons together, this first one is, in our case here, is kind of an artificial summary, which is the only thing useful here is telling us what the total flux density is basically of the sources. For the rest, this is kind of a non-real artifact in terms of like source apparently projected size, etc. But remember, we clicked on three separate sources which we wanted the individual objects for. And so this is given by, this one is our sort of extended, the first polygon we selected was our extended head-tail galaxy. So this is the information about that. The second one is, this is a central nuclear source, 2 millijanskis. And then the other source here is the little diffuse background galaxy. The total flux, sort of trying to guess that this thing is probably a point source because it just, the total amount of signal isn't very much bigger than the beam size. By the way, one of the things we do here is in order to get flux densities for anything, we have to know the beam major axis size and beam minor axis size and the pixel values, because to normalize our integrated, we actually, to get our flux densities, we sum all the individual pixels inside the polygon defined areas. And then to normalize that, we have to divide out by the number of pixels per actual synthesized beam. So the summation, so to normalize and get flux densities out, you just divide the sum number of pixel values inside one of the polygons by the actual B major times B minor thing, which these days is mostly contained as part of the FITS file. Way back when, in distant historical times, often the B major and B minor were only included in the history section of the FITS file, and there is a little utility program in our system, where you can insert B major and B minor if you as a system has to know those values if we want to get flux densities. Now, in this case, where I click the individual values or the three objects, we get this extended. We get this sort of structure with the super polygon, but we want to just look at the individual objects. Now, however, if we look at one of the things where we just clicked on the individual polygon. Come on. Now, this is one of the things where we looked at the cluster. If we only have one area in the cluster selected, then the whole thing is just included in the single super or one polygon thing. So this is the flux density that we calculate in the center region with a convolved beam of about 14 arc seconds or something like that. And all the information about that is then just if you only have one polygon selected, then you get one single value back out. So it's just something to be aware of in the reporting about what parameters are being used and so on. And that, I would say, is basically about it.